Hi, good morning, everyone. Today I'd like to talk about 3D object completion and humans and computational models. My name is Eunice. I'm a grad student in UC Berkeley, and this work is done in collaboration with Jasmine Collins, and my advisor is Alison Gopnik. So, object completion or three-dimensional objects pose a challenge in our visual systems because oftentimes we can only see them in a very limited 2D viewpoint, and we cannot see like the opaque backsides of these objects. But despite this very fragmented world, we're still very able to recognize and represent objects in 3D ways. And so the question is, how do we do that? There are studies, this is done in infants, suggesting that even from the age of 6 months, if you show them a very limited viewpoint of an object, something like a triangular wedge here, and that's only pivoting at 15 degrees, and then you give infants two different kinds of options of what the rest of the objects might look like, so either a complete volumetric display or an incomplete volumetric display. Infants would look longer at the incomplete test display, suggesting that they already kind of believe that objects should be of a full 3D volume. And so that's just one kind of evidence that's taken in infants, and it's a very passive-looking time account. So what about children, adults, and neural networks? Do we represent 3D objects also in full volumes? And can complete volumetric display preferences be generalized to more diverse and complex objects as well? So to answer these questions, today we have a roadmap involving 3 different kinds of studies. So the first one is on volumetric completion preferences, which is kind of inspired by infants as well, but we're looking in a broader population that includes older children and adults. And we also did some studies on symmetrical completion preferences, and also we're looking into how object exploration might also impact object completion preferences as well. So here are our participants. We have children between 4 to 7 years old, adults between age 18 to 40 years old, and we also are looking into a ResNet 50 neural network structure, which is a very state-of-the-art kind of computer vision model. And we have 3 different types of ResNet 50, the first one being a supervised ResNet 50 that's trained on ImageNet, the second one being a self-supervised version of it, which learns from data augmentations, and the third one being an untrained ResNet 50 as a random feature baseline model. And so with our first study, kind of like the infant study here, we will show participants a limited viewpoint of the object as shown on the top, and then we provide participants with 2 kinds of options. So one that is a complete volume, and another that's like an incomplete volume, as you can see in the bottom. And we do this with different kinds of abstract 3D objects that are downloaded from Thingy 10K, and we edited it on Blender. So here's the experimental paradigm for children. And basically what we do is we introduce children to a toy store where there are 2 characters, Teddy and Spotty, who are exploring different kinds of toys. And all of these toys are too high up on the shelf, so Teddy and Spotty cannot reach any of them. And we ask children to help us figure out what these toys might look like if they're turned around. So here's an example of a trial. So we'll have an object on top on the shelf from a limited viewpoint, and it's static. And then what we'll ask the children is, if we take this toy off the shelf and turn it around, will it look like 1, 2, or 3? And so what you see here in 2 is a distractor option. We just want to make sure that kids are understanding the task. And 1 and 3 would be the kind of difference we're interested in, whether or not kids and adults are representing objects as complete or incomplete volumes. And regardless of what participants pick, they'll always get an encouraging animation. And this is just to get them going without shaping their responses. For neural networks, what we do is we take image features from the query image, which would be the static limited viewpoint, and then we compare those image features with the choices we have. And whichever option has the highest cosine similarity would be reported as the model's choice. So here are the results. First, we computed an object completion accuracy, which is basically just out of the 12 trials that we have for all these different objects, how many times did the participants not choose the distractor option? In other words, how well are they understanding the task and kind of completing objects in a very plausible manner. And what we see here is that for both children and adults, they are computing or completing this task in a significantly above chance accuracy. Since there are two possible options out of the three options that are provided, chance level would be at 66%, which is indicated by the horizontal line, and we see that our humans are significantly above that. And for neural networks, at least with ResNet 50, they seem to be doing really well as well. For complete volumetric preference, we compute this by first deducting the trials in which distractors were chosen, and out of the trials in which possible options were considered, how many did we choose the complete volumes instead of the incomplete volumes. And so chance level would be at 50% because there are two possible options and participants choose one. So we see here that children and adults are significantly preferring complete volumes instead of incomplete volumes. And we also see that for the neural networks as well. And critically, adults show a stronger complete preference, complete volumetric preference, suggesting that maybe with age and experience, this preference might be strengthening. So that's complete volumes versus incomplete volumes. What about other priors or expectations in completing 3D objects, such as symmetry? And you might be wondering why we want to think about symmetry. Well, there's a very early preference for symmetry in humans. Infants can already habituate sooner to symmetrical patterns instead of asymmetrical patterns. There's also cognitive advantage to realizing that one half of an object is the same as the other half. It allows objects to be processed quickly with a less information load. And many of our natural objects and artifacts in our everyday lives are also symmetrical in some ways. So we're curious, if we just see objects from limited viewpoints, would we already expect them to be symmetrical as opposed to asymmetrical in its 3D form? So here is our study 2, which basically has the same paradigm as study 1, but instead of showing complete and incomplete volumes, we're curious what children's or adults or neural networks preferences are for asymmetrical options of these limited viewpoints versus the symmetrical ones. And with symmetry, we kind of try to do different kinds of asymmetries. So we looked into shape, size, color, and texture. And so what you see here critically is that the asymmetrical options are different in all these different manners. So on the top left, we'll have an asymmetrical option in terms of shape, and then on the top right, it will be an asymmetrical option in terms of size. So you can see that one half of the size is different from the other half. And then we'll also have an asymmetrical option for the color in the bottom right, and then an asymmetrical option for texture in the bottom left. So here are the results. Again, we compute object completion accuracy, which is just out of those all the trials we tested, how many did participants not choose the distractor option. And what we see here is that adults and children are significantly preferring and choosing the possible options as opposed to the impossible options. So they're doing really well. And for neural networks, for the self-supervised and supervised neural networks, they're also completing objects well, but for the randomly initiated neural network that's not trained on any sort of data, it seems not to be doing as well. And we think this might have to do with the fact that the symmetrical possible options and like the asymmetrical possible options and the distractors might be more similar to each other, so harder to distinguish without any sort of data training. And this is symmetry preference, which is just out of those trials in which possible options are chosen, how many do people or neural networks choose the symmetrical options rather than the asymmetrical options. And what we see here, chance level is at 50%, is that children and adults prefer 3D objects to be symmetrical as opposed to asymmetrical. And this preference is stronger in adults for texture, size, and shape. For neural networks, even with training, we don't see too much of a significantly above chance preference for symmetry preference. And what's interesting here is that if we look into the ages between 4 and 7 for children, we can see that symmetrical preference also increases significantly across age, again suggesting that this kind of preference in completing 3D objects might have to do with experience and exposure to different objects as we age as well. So there could be other possibilities why people might be choosing the symmetrical options other than the asymmetrical options. And so these are some possibilities we came up with. One is that they might just be matching how similar the limited viewpoint is to the other sorts of options. And so what we did here is we computed a 3D and 2D F-score of just outlining the geometrical similarity of the options and comparing it with the static viewpoint. And what we see here is that there's no correlation between the F-score, which is just how geometrically similar the options are, to the static limited viewpoint. And we also tried to do a kind of texture or pixel-wise similarity comparison using the SSIM metric, and again, we don't see that kind of correlation. It could also be that people are just choosing based on how symmetrical the limited viewpoints were to begin with. We had some limited viewpoints that looked symmetrical and also some that didn't. And here we didn't see any sort of correlation between how symmetrical the limited viewpoints are and what people are choosing. So it seems like people are really trying to complete 3D objects in a symmetrical manner. And so with that, we have a recent follow-up study where we're curious if exploring objects would influence object completion preferences. And in particular, we're curious, for instance, if playing with hollow objects before doing this task will lead to preference for hollow object completions, because that might suggest that it's about experience and exposure to objects in our everyday environments. So what we did here is we 3D printed some novel objects, and we showed them to participants from a limited viewpoint, as you can see here. But if you really play around with them and turn them around, you realize that they're actually hollow. And what we did here is we showed kids these different objects and told them to just play with them anyhow for about a minute. And then afterwards, they go on to do the exact same task as I've shown earlier. So this is an example of a participant, a 6-year-old female, playing with these objects. And what's interesting here is that for these hollow objects, she's really trying to put them together, suggesting that the prior for having objects as complete as opposed to hollow seems to be really strong, to the point that you want to put hollow objects together to try to make them complete, even though you can't really, they're not really able to be pieced together. And so, yeah, here are some preliminary results where we can see kind of the idea that playing with hollow objects, which is labeled hollow exploration on the x-axis, seems to be leading to a lower complete volumetric preference compared to children who did not play with these hollow objects. We are also trying to do another study where we have the exact same objects, but the solid versions of them. So we have them in black here, and basically we're doing the same thing and having kids play with them. And what we see here more is that kids seem to be rotating these objects a lot as opposed to piecing them together. And we're curious because we think that the limited objects, these novel objects and their hollow versions and solid versions can serve as like controls for one another. And we think, or we hypothesize, that there might be significant differences in the object completion preferences between the two conditions, depending on what kinds of objects they play with. So more results to come. Yeah, and to summarize, what we found from all of these studies so far is that children and adults and neural networks also show kind of a high above chance object completion accuracy. And this again is just out of the trials that were chosen, how many did you not choose an impossible distractor as opposed to other possible options. And it also seems to be that children, adults, and neural networks could represent objects from limited viewpoints as complete volumes as opposed to incomplete volumes. And children and adults, or just humans in general, also seem to be representing symmetrical objects as opposed to asymmetrical 3D objects. Whereas for neural networks, we don't really see that, suggesting that maybe incorporating some kind of data or training for 3D object kinds of symmetry preferences might help us improve computer vision. So what actually drives these 3D object completion preferences? One thing we see is age. As age increases, it seems like there's stronger preference for representing objects in a symmetrical and complete way. It could also be the data. Neural networks were trained on these 2D data from static limited viewpoints, and they don't show as strong of a symmetrical preference as humans do. And kids who were playing with 3D objects before these object completion tasks seem to be showing different kinds of preferences as well. So with that, I'd like to thank my collaborator and my advisor, my RAs, and all the participants. Thank you.
Thank you, Eunice. We have about 5 minutes for questions.
Thank you for the very interesting talk. So I was wondering about the neural network part. So the task you asked the neural network to complete is sort of different from what you asked for humans, because in the middle of the talk you refuted the hypothesis that they are doing similarity matching, but the neural network is essentially doing the similarity matching using a different metric instead of the SSIM. So I wonder how would you ask the neural network to complete the shape instead of just trying to find, and maybe that's something that why it didn't perform so well in the symmetric task.
Yeah, that's a very valid point. I think the neural network's data, based on how we computed it, further refutes the idea that we're just matching based on geometrical similarities. And with ResNet 50, it's trained on 2D image data set, so it's hard to get a 3D representation out of them. But one of our next steps is to consider 3D reconstruction networks, and hopefully we can really get at the question of how neural networks are completing objects in a 3D manner. But what we can see here from these data is that definitely 2D kinds of training is not enough.
Right.
Yeah, thank you.
Thanks.
Hello.
Hi.
Very good talk. I hail from a machine learning, more oriented background, and he kind of actually touched on my question, so I'll try to sharpen it a little bit more. So just to clarify about the architecture that you used, you said ResNet, and again, I apologize if I missed this detail. Was it trained, to your data, or you said that it was pre-trained? That's kind of one question. And then part of that question is, did you consider the architecture as a result as well, in the effect of finding these representations and the type of self-supervised training that you did? So self-learning is sort of like you're taking the data and doing manipulations to it and trying to do contrastive learning. So did you have a scheme? What was that scheme? And again, answer what pieces of these that make sense to how it affects these representations. I know you said you'll do follow-up work to get better, because my other question was about encoding priors, but you answered that. So could you enlighten us a little bit more about the ResNet component? Was it pre-trained? Did you tune it? What was the self-supervised learning scheme? And did you consider alternatives to perhaps improve your results in getting the neural net to line up with human data?
Yeah, we just took one of the more popular neural networks, I guess, and they're all, at least for the trained neural networks versions, they're all trained on 2D ImageNet. So we didn't do any sort of specific tuning to 3D object data, which is also something we want to look into, because it might be that all you need is the data and not even the structure to get neural networks to behave like humans and complete objects in a 3D manner. So yeah, that's a really good question. And then, so I guess one big question about all of this is it about the structure or about the data? Because what we have is really just one sort of neural network structure. We also tried it with SimClare, and it's not showing any kinds of significant preferences. So what we might want to do, also kind of addressing back to the earlier answer, is to consider 3D reconstruction networks.
Sure.
Yeah.
Just to clarify,
Yes.
so when you had self-supervised, that was a pre-trained network that was self-supervised trained, right?
Yes, yes.
Okay.
And both of them were trained on ImageNet.
Okay, so by pre-training, that might have also perhaps affected those representations. You might want to consider a self-supervised scheme, just training the architecture from scratch.
Yeah.
Even though that's expensive, it probably will get closer, in my opinion, to the human data that you're looking for. So, thank you.
Thank you.
If there are online questions, I can wait.
There are no online questions. Go ahead.
So, very interesting talk. Thank you very much. I totally believe all the results. But I have this generic concern that in many experiments, you build in the results by the choice of stimuli that you have. So I wonder if you had chosen other objects that tend to kind of lend themselves to hollowness, things like cups and basins and goblets and plates and saucers and those things. They are things that are meant to be hollow, and kids have experience with them. Maybe you would get exactly the opposite results. And so the question is, have you considered this? Did you run controls in which they are cups and goblets mixed in? A more informative design would have been if you have some kind of mixture of things, and then if there is a bias, it would be even stronger. So what about that? So is that something that has been on your radar as you do this otherwise very nice research?
This is a really great question. What we try to do is just randomly grab abstract or what we think are novel objects from Thingy 10K. So we try not to imply or suggest any kinds of like artifacts or functions to these objects. We just wanted to know, okay, if you see a new object without any sorts of assumptions, other kinds of assumptions, what would you think the objects would look like in their 3D views? But definitely, I think that if you, or if we show objects that are like plate lights or cup lights, kids are more likely to think of them as hollow than full volumes.
Thank you.
Thank you.
Thank you. Let's thank our speaker again and welcome our
Thank
next
you.
speaker, Ekaterina Shirkova.